Welcome to this explainer. Have you ever looked at a sheer drop? Maybe it's a crazy steep mountain road or one of those absolutely terrifying roller coasters, and you just felt your stomach completely drop simply by looking at the angle? Well, today we're going to bridge the gap between that intuitive, real-world feeling of a steep drop and the rigorous, honestly kind of beautiful mathematical formulas of analytical geometry. Okay, let's dive right in because we are going to completely demystify the equation of a straight line. I want you to imagine standing at the top of these colorful theme park water slides on a blazing hot summer day. Now, intuitively, without writing down a single formula, you already know exactly which one is going to send you flying down to the water the fastest, simply by looking at its steepness, right? You compare the yellow slide to the red slide, and your brain instantly calculates that angle. So the big question is, how do we take that gut feeling of steepness and, lock it down into precise, measurable math? Well, in analytical geometry, this steepness is universally represented by something called the slope, and we denote it with the letter m. Think of it as the engine driving our core linear equation, a times x plus b times y plus c equals 0. As long as a and b aren't 0, this formula absolutely guarantees a perfectly straight line. And that slope, our m, well, it dictates just how aggressively that line angles upward or downward. Now, to actually calculate this exact slope, we've got two really powerful methods in our toolkit. Method 1 relies on physical distances. It's the vertical change divided by the horizontal change, which you probably know as rise over run. Method 2, on the other hand, introduces a trigonometric perspective, calculating the slope simply as the tangent of theta. So that gives us a totally different, angle-based approach to defining the exact same steepness. But to use that second method, we have to be incredibly precise. Theta isn't just any random angle. Actually, scratch that. It's not random at all. It is exclusively the measure of the positive angle which the straight line makes specifically with the positive direction of the x-axis. By standardizing this, basically measuring counterclockwise from the right side of the horizontal axis all the way up to our line, mathematicians everywhere guarantee they're calculating the exact same slope. And look at how these two methods unite perfectly here. The dotted lines showing the vertical drop and the horizontal run, while they give us our physical distance ratio. But look right where the solid line intersects the horizontal x-axis. Boom! There is our angle theta, nestled perfectly against the positive x-axis. It's a real visual proof that the ratio of the sides of that right triangle is literally the exact same thing as the tangent of that angle theta. Two methods, one really elegant result. So moving forward, we have two main study goals: finding the slope and y-intercept if we know the equation, and finding the equation if we already know the slope and y-intercept. Let's tackle that first objective right now, finding the slope of the straight line and the length of the intercepted part of the y-axis. And we'll kick things off with a concrete prelude example. So we are given the relation 2x minus y plus 3 equals 0. Now, to represent this graphically, we literally only need to find two distinct points that satisfy the equation. That's it. Finding those 2 points perfectly defines our line in space, giving us the anchor we need to actually graph it out. Now, I'm passing the baton to you. Knowing we need just 2 points to lock in that straight line, how would you mathematically uncover them for the equation 2x minus y plus 3 equals 0? Seriously, grab some graph paper, maybe try plugging in a 0 for x, and just see what happens. Can you determine the steepness of your own line once it's drawn? Well, until next time, keep calculating, and I really hope this explainer helped you see the cool math hiding right behind the steepness.